All right, here we are, day one, term 5, and this is geometry. We've just been talking a little bit before we started here about what the course consists of, how many units there are, how the grades are going to be arrived at, and that sort of thing, how Google Classroom works. So for now, we're going to dive right into this first handout that you would see in your Google Classroom materials. And this is one of those things that if you need a hard copy, of course, you're welcome to print it out wherever you are. But if you need a hard copy and you can let me know, I'll make sure that it's available for you, even if you're not able to come into the school building when I'm here, since I'm only here Tuesdays and Thursdays. I'll make sure that it's here somewhere. Your coach will have it. So if you have trouble taking notes, and I'll tell you, in this class, taking notes is really, really important because of the volume of material. And it starts right off with these definitions. One of the things that you'll learn as you go through geometry is, like a lot of math stuff, it's you know, you start to build a foundation and then everything gets layered on top of that. Well, these definitions are where this all starts. And geometry has some sort of unique characteristics in some sense. You got some definitions that maybe aren't common sense definitions, but they are mathematical. So you have to make sure that you understand the math definition and not what you just might be thinking of just in normal everyday life. And a perfect example of that is when you get into this very first section here. And I'm going to pause this for just a second. When you look at the definitions here, point, line, plane, collinear, it might not even make sense to say that a point is a location with no size or shape. Well, practically speaking, you can take a pen or pencil and you can draw a point on a piece of paper, but it's truly a theoretical concept. Line is similar. It's made up of points. It's got no thickness or width. Okay. The other thing that you'll notice about geometry is the way these examples are shown to you graphically. So there's a lot of things that you'll have to understand just from how a drawing is labeled. For instance, these points here are always shown by capital letters. So if you see, if they don't tell you that somewhere in a problem that you're looking at, you're expected to understand that and to remember that already. So this is point A, point B, point C. When you look at the next one here for line, well, that's line XY, and the graphic representation is that XY together with a line over the top of it that has arrowheads on both ends. Line is one of these things that goes on forever in both directions. That's why it's got the arrowheads on both ends. Lines can also be shown by a single lowercase letter. So if this had another letter somewhere, we could say that was line A, for instance. We could identify it that way, but we don't have that right now. We just can only say this is line XY. You can see right away that what I have here is in a little different order than what you guys have. Plane and collinear are next. Plane, it's a flat surface. It's made up of points and it extends indefinitely in all directions. This is another one of these theoretical things that extends forever in all directions. The thing about planes, if you look at this, they're trying to make it look like a sheet of paper somewhat, or the top of a desk, or some surface that's flat. If we're going to identify this plane, we have to use 3 of the letters. We have to identify it by 3 letters that go with points that are on that plane. Any 3 will do, doesn't matter. As long as they're on that plane, we can use any 3 of those letters. Think about a chair with 4 legs is quite stable. A stool with 3 legs is still pretty stable. But if you go less than that, 2, I guess you could have 1, it's not nearly as stable. So that's part of the reason why, if you think about holding a sheet of paper on 3 fingers, let me see if I can do that. So if I'm going to hold this sheet of paper up with 3 fingers, it's hard to see with the green screen there, but 3 fingers, still pretty stable. But if I try to do it with only 2, it falls right off my hand. That's why we got to use 3 letters to identify planes. Collinear means they're on the same line. The opposite of collinear is non-collinear. You'll see this first homework that goes with this has a lot of this kind of question in it. You know, which would name 3 collinear points. Name a point that's non-collinear with line Z, for instance. So when I'm suggesting that these definitions are important, part of the reason I do that is because they're not just important for what you're doing in this unit. These definitions are going to come back again and again and again throughout the whole term. So these are some things that you should keep handy. Keep them close by. Anybody got questions so far? One of the things I've always liked about geometry is that it's much more of a visual subject than, say, algebra, because you can draw pictures. So after collinear comes coplanar, points that are on the same plane. Makes sense. Non-coplanar, points that are not on the plane. So P, Q, and R in this little drawing, they are on the same plane. This other thing here in the corner, this capital B, this kind of fancy capital B, that's the alternate way to identify that plane. We could call it plane PQR, or we could call it plane B. That big capital B there, it looks like it's maybe written in cursive. That's not a point. That is another way to identify a plane. Line, segment, and distance formula. So again, these are not in the same order. There we go. Line segment. Measurable part of a line. The big difference between lines and line segments is segments end. We could measure this segment here, RS. We cannot measure that line XY, because that line XY goes on forever in both directions. RS has a starting and ending point. And if you look at the graphic, the way it's described, that's different also than the way the line was. It's just a flat line over the top of the letters. It doesn't have any arrowheads on it. So if you're told in words, and you'll see some word problems that will do this to you, you know, line segment RS is blah, blah, blah. Well, you have to know how to draw that out, and it would look like this with two endpoints. So if you were asked what's the difference between a line segment and a line, the easy answer would be line segments have beginning and endings. Lines go on infinitely. And the way they're shown graphically is different. The next thing on here, distance formula. Distance formula. This is one of those formulas that you will see used quite often in a lot of different situations. And if you notice underneath this big hook symbol here, that's a square root symbol. That all of these operations that are underneath there are going to end up getting square rooted. If you haven't done much with square roots, your calculator on your phone is going to need to be turned sideways. Calculator in this orientation is only going to give you adding, subtracting, multiplying, dividing. When you turn it landscape style, and mine didn't rotate. Why is that? I probably got it off. Yeah, there we go. Landscape style. There we go. Now it changed into a scientific calculator. And I have an Android phone. A lot of people have iPhones, I know. And all these calculator apps are different. On mine, the square root symbol, the little bitty check mark there, it looks like a check mark. So if I look at the square root of 45, I put the square root symbol in first and then hit equal at the end of it. I get, well, you can't even see that. Sorry. 6.7082039324993. Square roots almost never come out even. So you're going to have to learn how to use a calculator to get square roots. Now, when I was in school, we had to learn how to do square roots by hand. Thank God we don't have to do that anymore. You would hate it. I hated it then. I wouldn't want to do it now even. I don't even remember how to do it. But every calculator's got a square root function. And the only square roots that you can find that come out even are called perfect squares. If you were in my algebra class before, you might remember me talking about that. Well, what's a perfect square? It just means a number that you can square root evenly. Perfect squares: 4, 9, 16, 25, 36, 49, 64, 81, 100. Square root those, and I'm going to get an even number. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5, etc. So get used to using the square root when we're talking about the distance formula, because you probably also heard me say graphing on an XY coordinate plane started in geometry, and then was taken into algebra by René Descartes. So blame the Frenchman for that 500 years ago. And you can see from the way the formula is put together, it's X and Y coordinates. So if you think back to when we were just graphing individual lines on an XY coordinate plane, if it's a flat line or it's a perfectly vertical line, those are easy to figure out the lengths because then you can just count the squares on the graph. It's the diagonal lines, the lines that aren't perfectly straight up and down or perfectly horizontal, that we have to use this distance formula on. Now, if that doesn't make sense, I'll show you another way. Because the distance formula is actually a variation of the Pythagorean theory. Anybody remember the Pythagorean theory? Yeah, a squared plus b squared equals c squared. So I got this shape here that I'm drawing on my XY graph. Looks like a triangle. If I wanted to know how long, let's say I want to know the perimeter of this triangle, well, I'm going to have to measure, figure out how long this line, this side is, how long this side is, how long that side is, and then add them all together. Well, because it's on an angle, I can't just count the squares. If you think back to what the Pythagorean theory gives you, a squared plus b squared equals c squared, gives you right angles, right triangles. Okay, so what we're actually using the distance formula to do is to calculate that angled side. Okay, so that's what we would have to do here, and for this side, and for that side. So it can be a messy calculation that you have to do repeatedly, but that's okay. It'll get you used to using your calculator and doing square root functions, because you're going to end up with points, x, y coordinates that you're plugging into this calculation. You're going to have to square the differences, add them together, and then square root the whole thing. This is one of those formulas. I won't expect you to memorize this formula. Keep it handy though. Be sure you know where to go to find it in your notes. I know at least one of the tests, I included this formula at the very beginning of the test as a reference, you know, because I don't want you looking it up necessarily while you're doing the test, so you can concentrate on getting the answers. So any questions about that, the distance formula? All right. Congruent segments. Let's find that. There we go. Geometry, this word congruent. Congruent or congruency. See, it'll end with a CY sometimes. Congruent segment means segments are exactly the same length. Later on, we'll be talking about congruent triangles. Well, congruent triangles have to have the exact same angle measures. They have to have the exact same side lengths. They have to be exactly alike. But with congruent segments, we're talking about a measurement. So here you can see AB is 7 inches, CD is 7 inches. The orientation doesn't matter. Then right below this is more of this sort of graphic representation that you might have to interpret. if AB equals CD, then segment AB is congruent to segment CD. So this symbol here in between, shoot, that symbol in between your segment identifiers looks like an equal sign with a squiggle over the top of it. Anytime you see that, you know you're talking about congruency. And you'll see that symbol used again and again and again. Questions, anybody? Midpoint formula. Another one of these formulas that we'll have to use for calculations. Again, something that's on the coordinate plane. You can see the X's and the Y's here. Those represent XY combinations. This is the formula that's used to find the midpoint between two endpoints. This is another one of those situations where if we have our graph, we have a line that's on this sort of angle. Here's an endpoint. Here's another endpoint. We want to know, let's see, I'm going to eyeball this, but we want to know what the coordinates are at that point that's right smack in the middle. Yeah, that's not even, it's not even in the middle. It looks like it's, but I don't have a scale on here, so it's kind of hard to tell, but I'm just, like I said, just trying to eyeball it. If that was straight up and down or straight left and right horizontal, it'd be easy. You just count the squares, divide by 2, right? Well, because it's on a diagonal, we can't do that. We have to use this midpoint formula. And you can see that both, it's basically an averaging, right? Because you're going to add the two x values together, divide by 2, add the y values together, divide that by 2. That's going to give you the xy coordinate for that spot that's right in the middle. So you're coming up with an average. The harder sort of problem to solve is when they give you the midpoint and one of the endpoints, and you have to find the other endpoint. We'll work through some of those here fairly soon. Segment bisector and ray. Segment bisector. If you're not familiar with that word bisector, get used to seeing it. It means you're cutting something in half. 2 equal halves, 2 congruent halves. In this case, they're taking a segment of this graphic over here showing you we've got segment AB and line L. Remember I said earlier that lines can also be identified by a lowercase letter? Well, there's only one point that's shown on this diagonal line here, so they're calling this one line L. That's the bisector of AB. So when you bisect something, you're cutting it into 2 equal halves. That point of bisection is the middle. That's the midpoint. I think that's why they labeled this with M, because that refers to the midpoint of segment AB. So if you wanted to figure out dimensions for the whole line, you'll see problems like that. They might give you this and this with the distance. But the other thing that you would also see is segment AM is going to be equal to segment MB, right? It's AB that's cut in half, M is in the middle. So segment bisector, just the idea of a bisector is something that you'll see again later on when we start talking about angle bisectors also. So let's see, the last on that section was ray. You can call me Ray, you can call me Jay. Just as long as you call me. You guys are too young to remember that commercial probably. But if you Google it, I'm sure there's on YouTube plenty of those commercials. You can call me Ray. Okay. Ray here is, think about a ray of the sun. It starts at the sun and it shoots off into space infinitely. The sun, of course, is in all directions. For us, a ray is just having a starting point and it goes in one direction through another point. And you can see the difference in how it's defined or graphically shown here also. The EF here for ray only has one arrowhead. Remember, the segment had no arrowheads. The line designation has double arrowheads. So if they don't tell you in words what something is, this is another reason why you got to get used to reading and understanding these little graphic ways of showing different pieces and parts of this stuff. Double arrowhead is a line, no arrowhead is a segment, one arrowhead is a ray. Now, a lot of people probably think about geometry in terms of angles, and that's as it should be. An angle, believe it or not, is actually the intersection of two rays at a common endpoint. So here we have ray BA and ray BC. The thing you have to get used to here, especially if it's written out by hand, this designation, this symbol here, ABC, that's not an L. That is how you show angle ABC. Okay, so right at the beginning today, I said, you know, you're going to have to get used to how geometry represents things graphically. Here's another good example. Angle ABC. The vertex, another important vocabulary word. The vertex is where the sides of the angle intersect. The other thing that you'll come to learn about angles and when you describe them, this vertex letter, if you're going to describe angle ABC, because those letters are in that exact order, I know that angle B is the vertex. That's the convention that mathematicians use. The vertex has to be in the middle of your description. So I could say that this is angle CBA or angle ABC. It's the same angle. It's just described a little bit differently, but the B is still in the middle. The B is that middle letter of every angle description is going to be the vertex. Really, really important, because we can't say CAB. That's something different. The vertex letter is always that letter in the middle. And what you'll learn is the order matters. The order is really important, especially when we start looking at two different, say, triangles or comparing angles to see if there's congruency. The order that these things are listed in is extremely important. and you can rely on it. If I didn't have that graph right there, that drawing, and all I had were these letters, angle ABC, I could confidently draw ABC in that angle measure, and it should fit this. Might not have the right size or the right number of degrees in it, but I at least would be able to draw it and visualize that angle ABC, because I know that B is in the middle. B is the vertex. Right angle. You see that little box here in the corner? You know you have a 90-degree angle. That's what a right angle is. We can't build anything that is square without using right angles. If you think about where the wall in your room and the floor come together, that's a 90-degree angle. Look at the corners of the desk that you're sitting at, 90-degree angles. Pretty much anything that's constructed is going to have walls and floors that are at 90-degree angles. Now, a roof might not be at a 90-degree angle. Around here, it's going to have some slope to it because we got to have the snow melt off. But you might go to Arizona or New Mexico or out in the desert, and you have a lot of places out there where the roofs are basically flat. They're not perfectly flat, but they're pretty close to that. 90-degree angles are everywhere. And sometimes they're not going to tell you, but they're going to show you it's a 90 because of that little square that they stick in that angle, in the corner of that angle. Acute angles, obtuse angles, these are two measurements that people get confused all the time. So get with somebody if you have to and practice these definitions, because when we start trying to figure out how many degrees some angles are, you have to know, if they tell you it's an acute angle, automatically you have to know that that's going to be less than 90 degrees. See, the thing about right angles is they are always exactly 90, not 89.9, not 90.1, 90 only. So right angle can only have that square. That's the only kind that you'll see this. Acute angle is everything less than 90. Obtuse. So if you look at that angle here with the drawing with the acute angle, it's more of a closed angle. Obtuse is more than 90, and it's more of an open angle. So those two definitions, extremely important. Now, I don't think you guys have the next one on there, and I don't know why that was left off of the student example, but I always talk about it anyway. This third one, or this fourth one, straight angle, an angle with a degree measure of 180 degrees. Well, that's just a line, or a line segment even. If I have a circle and I draw a line straight through the middle, the very center point of that circle, all the way across, that's where you get the 180 from. A circle has 360 degrees. When you cut a circle in half, you get 180 degrees for the angle that's made up of the circle, and for the remaining half of it, and for the line itself that cuts through it. So you're actually talking about the diameter in that case. But for us, a straight line has 180 degrees. And that is important to remember anyway. Congruent angles. There's that word congruent again. Two angles that have the same measure are congruent. Well, what do we measure angles with? Degrees. Angles are always measured in degrees. And down below the drawings, you've got some more graphic information about how these things are described, where you have to understand what the symbols mean. If you didn't have the drawings, You have to be able to read what I've highlighted here and understand what it is. That little m here, that stands for the measure of. So if the measure of angle A equals the measure of angle B, then angle A is congruent to angle B. This is one of these sort of logic statements. People that do geometry call them proofs. It's an if-then sort of statement. That's why I read it that way. If the measure of this equals the measure of that, then they are congruent. We'll get more into proofs later on, but that's a very common thing that you see in geometry. We haven't measured these angles, but they tell us that they're both 43. So that means that the measure of each of those is the same, which means they are congruent. And again, they've got that little congruency symbol in the middle. If you notice, when we're talking about a measurement, we're going to use an equal sign. When we're talking about something that actually has a measurement, whether it's centimeters or degrees, if the measurements are the same, then we can say that they're congruent. Congruent angles. Adjacent angles. Two angles that share a common side and vertex. They're just next to each other. And the drawing here just shows you a couple of angles, 1 and 2. We don't have any other information. That's the other thing that you'll learn about geometry, is you really cannot assume anything. To the eye, angle 1 and angle 2 kind of look like they might be congruent. But I don't have any way to measure that. I'm talking about this drawing right here. I don't have any way to measure that. There's nothing in that description that tells me that they're equal. I cannot assume that they're congruent. All I know is that they're next to each other, so they're adjacent. I can't say anything else about them. Geometry is full of situations like that. You cannot assume anything unless it's shown, or you can prove it from what's shown. So, got to watch your assumptions on a lot of this stuff. Vertical angles. Vertical angle. You know, normally if we talk about a vertical line, it means up and down. Vertical angle is a little bit different. This deals with where we have two lines that cross. The angles that are opposite each other are always congruent. Always, always, always. And you see they've highlighted here with little stars. So angle 1 and 2 are congruent. Whatever the measurements are, angle 1 and 2 are congruent. Angle 3 and 4 are congruent. So if I knew what angle 1 was, I could find all the rest of those angle measurements. You will see a lot of problems like that. So vertical angles, this is one of the most important definitions that we've got in this first unit. The next two here, are they in the same order? Yep, okay. The next two, complementary and supplementary, are also ones that people get confused about. So be sure that you've practiced with these enough to know what complementary means. Doesn't mean that they're nice angles, that they have nice clothes on. You're not telling them that you like their hairdo. That's a bad dad joke, so sorry. But they add together to equal 90. Complementary angles always will total 90 degrees, and they don't even have to be adjacent to each other. In this drawing, they are adjacent. And they're showing us with this box in the corner that the total is 90 degrees. So contrast that with supplementary. Supplementary angles equal 180. People get those two mixed up all the time. Complementary adds to 90. Supplementary adds to 180. Now the one that follows this linear pair. This is another one of probably the most important definitions that you'll see in here. Because when we start having to figure out angle measurements from some of these complex drawings with lots of lines crossing each other, these are relationships that have meaning mathematically. Like the vertical angle here. If I told you that angle 1 was 100, then you would know angle 2 is also 100 because of the definition. Linear pairs like that too. Linear pair is two angles. It's a pair. When you combine them, they create a straight line, which means that it's a straight angle, which means that they're supplementary. So if I told you that that angle was 110 and this is a linear pair, then you would automatically be able to figure out that the remaining angle is 70 degrees. Linear pair, vertical angles, those two definitions you will use this entire term. So make sure that you have a good grasp on those. Perpendicular and angle bisector. Not in the same order. Okay, angle bisector. It's not any different than the line bisector. Only now we're talking about an angle that's being cut into two equal pieces. And this one is important also for the way this graphic is drawn. Because there's no words with this drawing that tells me that this is an angle bisector situation. But these little half circles here with the single dashed line that cuts through them, those are congruency marks. Understanding this drawing means this angle here is congruent to this angle. The only way that that can happen is if this line here in the middle is cutting the larger angle into exactly equal pieces. There's no words on there that tells me that. If all I had was this drawing, that's the conclusion that I would reach, though, because this is showing me as these two angles are congruent. If we had more angles that were congruent, we wouldn't have the same, necessarily the same single little tick mark is what I call it. If you have a rectangle or a parallelogram, not a rectangle, but a parallelogram, you might have other angles shown with two tick marks. Okay, those are the ones with two tick marks are congruent. The ones with one tick mark, those are congruent to each other. They're not all four congruent to each other, but this is a very common way of showing congruency when we're talking about angles. So get used to seeing that also. Perpendicular. Perpendicular, two lines that intersect at a 90-degree angle. So there's a couple of different ways that this can be shown graphically. You can read this drawing here as line L is perpendicular to line M. because the box there tells me it's 90 degrees. So if they're 90 degrees, automatically I know that they're perpendicular. Now, if we don't have a drawing and it's written out in words, this upside down capital T is the symbol for perpendicular. So if I wrote it out, it would say line L is perpendicular to line M, and I would use this symbol in the middle of that. Okay, I don't even think these next two are on your handout, but they should be. Perpendicular bisector, it's another one of these, is cutting stuff in half. And here's an example of where the two tick marks are being used, like I was talking about a minute ago. So I know that angle, or that AM is congruent to MB, and all of those angles around that are 90 degrees. Well, how do I know that? Well, they're vertical angles. So these two are congruent, 90 and 90, which leaves me with 180 split in the other two. So those are all 90-degree angles anytime you see perpendicular intersections like that. The big thing about the last one here I want to talk about for the moment is with parallel, you have another symbol. It looks like 11 or two L's right next to each other. Graphically, we have line L and line M here. If we're going to write it out in words, those two vertical lines right next to each other tell me that those two lines are parallel. So you can see there's a lot of symbolism used here throughout all these definitions. And whether you understand things better by reading the words or by looking at the graphics part of it, it doesn't make any difference to me, but it really have to be pretty comfortable working with both. And if you like to draw, make sure you draw some examples like this that will help you remember these things, these definitions. Questions, anybody? All right, the next page of that handout is another, it's a suggested note page. You don't have to use it if something works better for you, or if those definitions that we just went through work better for you. If you notice here, all they're doing is restating a lot of the things that were in the definitions. Right? So if you're looking here, what is a point? Well, what was the definition that we had? It's a location. A point is a location. It has no blank or blank. It has no size or shape. And we always use a capital letter to name a point. Point A, point B, point C. Okay, so if filling this out will help you remember some of these definitions, by all means do that. They're not looking for any new information here on any of this. It's the same stuff, just formatted a little bit differently. If down here under plane, this is a little bit better example of what I was trying to describe earlier with that capital letter that's in cursive, that capital letter P. It's a fancy stylized P. It's not the same font as K, J, or L. Well, those are points. And the reason I know that this is plain P and not a point, well, there's no point near it. That's one thing. And then the style of the letter tells me also that it's referring to the plane, not to a point. Now, this next section here at the bottom, could you fill in this blank here? Two lines intersect at a what? Anybody want to guess? Can you tell from the drawing what the intersection is? And what is P? P is a point. Two lines intersect at a point. Thank you. Very good. This other drawing here is a little bit harder to read sometimes. I know a lot of people struggle with this, because what we have there are two planes that are intersecting. So what they're doing, they're trying to show something in 2 dimensions that's actually 3-dimensional. And so these dashed lines that you see here are the parts of something that's hidden by something that's in the foreground. So if this line, or excuse me, plane L was a sheet of paper, you can't see through that necessarily, but this dashed line here represents the other edge of plane M. And then this vertical dashed line represents the part of plane L that's underneath plane M that you can't see. Sometimes you're going to want to create your own little graphics for this kind of stuff. But even from the drawing, you should be able to understand that two planes intersect at a line. Okay, that's what goes in that blank. Two planes intersect at a line. And you can tell that also, even if you're having trouble with the visual, look at K here. There's no point there. We can show a line, we can refer to a line by a lowercase letter. So that tells me that this line K is the intersection of those two planes. So being able to visualize some of this stuff in three-dimensional can be a little bit tricky sometimes. So the next page is practice, and the first homework is going to be similar to this. We're looking for 4 collinear points in that first diagram. Anybody see 4 collinear points? I got a suggestion here in class. It's not quite what I was looking for. Collinear, they got to be on the same line. There's only one possibility for that.
Oh, H-N-K-I.
H-N-K-I, right, exactly. That's the only, this line R here is the only one that's got 4 points identified on it that would satisfy this first question here, 1A. So a lot of these problems in the homework stuff that you'll see is exactly that. You've got to take a drawing, you've got to interpret it to be able to answer these questions. A line that contains point M.
A line that contains
Mm-hmm.
M-N-O.
Okay. What Audrey said was M-N-O. That is the line. Keep in mind here, and this is another one of these sort of geometry conventions, we only need 2 letters, 2 points to identify a line.
M-O.
So the tricky part for me as the teacher is there are a bunch of different correct answers for that problem. I could say line M-O, I could say line M-N, I could say line N-O, I could say O-N, O-M, NM, or I could just say line P. That lowercase p out there identifies the line also. And that's what makes grading some of your work time consuming for me. It's no big deal, but there are a lot of different answers, and I gotta look at the drawing just the same as you guys do to see if your answer meets the requirements, meets what's being asked. And it's also an example of where a definition, see if we go back to, whoops, let me go back to the teacher's version. The definition can help you with your answer. Because you think about this line example here, it's only showing you 2 letters, 2 points, and that's all you need to be able to identify a line. If you look at D, another name for line Q, well, okay, here's Q. That's another one where you could have multiple answers. But all I need is 2 letters, 2 representing 2 of the points that are on that line, and I'll have one of the correct answers. Could be JK, could be KL, could be LJ. So a lot of what you're going to see in this first homework assignment are interpretations like this. The diagram in number 2 might look a little bit odd. We've got a plane represented by this 4-sided shape. We got this line here that looks like it's on the plane. We got this other line that's going through the plane. And how do I know that's going through? That dashed line. That's a part that is being blocked. If this was in real life 3 dimensions, and I took a pencil and shoved it through a piece of paper, this dashed line part here would be the part of the pencil that I can't see below the piece of paper. So that's kind of what that line BE represents. So it's the same kind of questions. But look down here at 2E. What is the intersection of plane M and line K? Yeah?
E.
Point E. Very good. That's exactly right. Point E, that's the intersection of plane M and line K. Line K is this line. That point E is the one spot that is actually on the plane. And you know that because this top part of that line is visible. Then you get into the dashed line part that's not visible. That means that's gone through the plane now. Number 3 here, this drawing is one of my favorites. And especially when you look at 3D, how many planes appear in the figure? Audrey says 5. Anybody have a different answer? She's right, but I'm just curious if anybody has a different answer. Some people have said 6 in the past. But there are only 5. This is a 4-sided pyramid, right? You got this side facing you, another side over here. You got the side that's behind, and then the side over here on the left that you can't quite see. So there's 4 sides of a pyramid. The base of the pyramid is actually on plane R. So some people will think that the base is a separate plane. Well, it's not. It is on, it's part of the plane R. All these points here in the corners, those are on the plane. That's how you end up with only 5 as planes on that particular drawing. Okay, questions so far? I don't want to start the distance formula stuff today, but if you want to dive into that yourself, you're welcome to do that.
Can you do 3C?
Audrey's asking if we can answer question 3C in that diagram. The intersection of plane R and plane ZVY. Okay, where is ZVY? ZVY is this left-handed side of the pyramid. What do you think the intersection is? What part of that side is on the plane?
V.
And what else? It's not just point V.
Oh, V and Y.
VY. Remember, this goes back to definition here also. Where is it? Two planes intersect at a line. So that definition should help you remember that that whole segment right there between V and Y, that is actually the intersection, because you have this one plane that's going vertical intersecting with this other flat plane that it's sitting on. So it's not just a single point, it's going to be that line segment, that part of the pyramid. Any other questions? We are about out of time today. One thing I forgot to mention earlier, I really like when people keep their camera on. I can't require you to do that. I know some people are bashful about, maybe you just crawled out of bed, and that's perfectly fine. If you don't feel comfortable answering questions out loud, hopefully you guys are all familiar with this chat function. So if you want to give me an answer, you can choose me out of the list here, send it to me directly. Nobody else has to even see it. I mean, if you want everyone to see it, I think the default is to send it to everyone. But if I want to send something just to Mason, he's the only one that's going to see that message. And you can do the same thing with me if you'd rather. I mean, I don't want to call you out on something if you're not comfortable with it, but I do like the feedback. It's good for me to hear from you when you've got some idea about an answer, and then I can respond also, and then hopefully it gets us a little bit more interaction rather than you guys just sitting and listening to me. So use that chat function as often as you feel comfortable using it. Okay. See, today's Tuesday, Wednesday, and Friday. I'm going to be around. If you guys get stuck on something, the best way to get in touch with me is going to be by text. I'm not always at my computer, but I do have my phone with me all the time. I get in trouble for looking at it too much, but texting me is going to be the best way to get my attention. If we need to set up some extra time, we can do that. So appreciate you guys all being here today, and we'll see everybody on Thursday.
Or in 20 minutes or 10 minutes.
Oh, you're in my financial foundations too. That's right, Jonathan. Okay, good. Yeah. All right. See you in a little bit.